Okay, we continue our discussion about the review of the vectors and tensors on some other mathematical uh, concepts for the assistance of the transport phenomena to understand all the detailed physical meanings of the equation and the mathematical formulas and so on. Okay, so just continue to review the vector and tensor operations. We know from high school and vector is that has both the magnitude, scalar, and the direction. Can show uh, any vector by this form. When you go and check the literature, you can find many other ways to representing the vectors and tensor for in different ways. So it doesn't matter, all of them is same. In here, that one is the unit vector. We call it the direction of A. We call here any specific coordinates. For example, in here, rectangular coordinates, a vector is written in terms of three scalar components. Let's say we are in the three space. If we are in three space, now there are three coordinates and plus one. In general, we go x, y, z, and plus t for dimension and three space. And three base vector, then in three space, we have three direction. We can call x, y, z, either we can call x1 and x2, x3, doesn't matter, all the same. Also, we have three bases for this three space. We can call this base L1, L2, L3. There are also other representation of these bases in the literature. You can, for example, I here, J and K, and other things, U1, U2, U3, so on. So these L1 and 2, L3 are the independent of any position, and they are also orthogonal because they are perpendicular each other. So between the L3 and L2, the angle is 90 degrees. So dot product between these two is give the result of 0. Then we call this orthogonal each other. So let's continue. In the next slide, okay, if you continue our discussion, so in the rectangular coordinates, we can write any vector like this by this form, either by this form, either we can reduce this form. We see this form is called the summation convention. It's coming from after Einstein. So even we can reduce this form to this form. In here, the indices I is repeated, so we can repeat I like that A1 L1 plus A2 L2, and because we are in the three space, if we are in the more than three space, we should add some other terms here, doesn't matter. So we call this summation. We call the vector is the first order tensor. In second order tensor is represent like this in the power of 2 and has 9 elements. So any vector can be, tensor can be represented by the big A. So the elements of this tensor can be written in this form. We can reduce this form to that form. You see A, Rj and Li and Lj this time has 2 units because we are in the two order, second order. So in here, this is the reduced form of that one here. Also, third order tensor can be represented here in third power, and the representation of the third order tensor, we have 3 unit vectors inside of it. In here, ijk each appears exactly twice, you see, and we call this zero order tensor is as a scalar, and scalar. So let's move to the next slide here. In the next slide, we have an important concept here. We call it dot product. the dot product is the between two vector and AB is represented by here. It is the magnitude length of the A norm, or we can call the norm, or B magnitude or length of the B and cosine between these two vectors. Actually, this term here is the representation of the projection of the A on the B. Let's say we have projection of A on B, so we have another vector here, and this is the vector B. This is projection of A on the B, so we call this length by this length of A multiplied by cosine. So anyway, so just continue. Okay, dot product or inner product between the two vectors. If you present the vector A and vector B, because they are different vectors and we can put the different indices here, doesn't matter. So we obtain that one vector AB, and the unit vectors belong to A and belong to B, and dot product between them is give that one. We call this, I show in the previous videos, it's called this chronicle delta. This delta result is 0 if the I and j, they are not equal to each other, is give the result of 0. If they are equal to each other, then it's give 1. So in here they just for example, we obtain the one, and okay, now let's say we write AI and BJ, and we have that one. Now if I made I equal to j, because if any case I not equal to 0, it's gonna give the 0 result. And if I put the I instead of j, then I obtain that one, bi and ii, and this gives the result of 1. Then I obtain that one as a result. Either instead of putting the I can put j, then I can write ij, bj, and jj, and it's also same, is results 1, and I obtain that one. Even if I have another in this, let's say k, I obtain the same all L, doesn't matter. And dot product between the any vector and the tensor is similar manner. I obtain the dot product between two tensor. Again, I do the same thing. I set I equal to j, and I put the I and j, I instead of j, and I keep the k here, and I obtain that result and a dot product between the vector and the tensor, or that one. And a dot product between the first one is this time is the tensor, second one is the vector, and the result is given in this form. So okay, let's continue our discussion to the next slide. Actually, another operation is the dot product between the two tensor. Here I just obtain, let's say here, ij, b, kl, then I get li and lj, dot product between lk and ll in here. If I set j and k is equal to each other, then I'll obtain that one, and I then set g is equal to k, and it's gonna give the result that one. Then I can write aij and bkl in here. I exchange by the k by the j. I can write this form. This is the dot product between two tensor, and we call this second order tensor. In addition, we know from the undergrad, from the linear algebra course, we can add the two vectors and we can multiply them by the scalar addition of the two vectors given by this formula, and addition of the two second order tensors can be written in this form. Also, we can multiply the vector by the scalar a like this. We can multiply the tensor by the scalar of a. Okay, this is also good. So going next slides. In here, you see another uh, uh, sub title. Double dot product between two second order vectors give the result that I want. This is the a scalar. We know from the dot product, single dot product between two tensors provide second order tensor, but this time is provide a scalar as a result. Similar manners provide a scalar. Trace of the second order tensor. Let's say we want to find the trace of the a in the tensor. We can write the tensor by this form. Then we have that, and we obtain that one for the trace for tensor. That means, let's say you have some tensor is some 9 element, as I showed before. We can write this the 9 element in the matrix form, like here. According to the definition of the trace is the summation of these terms inside of your matrix, inside of in the 9 elements. So this is trace. We can write a11, a22, and can call this a11, a22, and a33. This is called the trace of your tensor. Okay. Okay, in here we have the term identity second order tensor. We can write the identity tensor by this formula. We have only just these elements, the other elements are 0. The dot product or inner product between the vector and an identity vector or tensor is to give the result of the vector itself. This is the same if you get the dot product between the unit vector or tensor and vector, it gives the vector itself. Similarly, if I try to get the dot product between the tensor and the tensor, is give the result of that tensor itself. Same, it is the same thing we can obtain from here. And the next one, now we just want to represent the dot product, inner product between two vectors in the open form. As we say, we are in the tree space. We have in tree space 3 elements in 3 coordinates. Let's say for the vector A, we have 3 elements A1, A2, and 3. This can be X, Y, Z in the rectangular coordinates, or other coordinate, they should have different. And for the B, we have 3. To get inner product or dot product between two vectors, we just write the first vector in the row form. In second one, we write just column form. Then we obtain dot product elements by element. We multiply the first elements and then plus second element's multiplication plus then third element multiplication. And the dot product between the tensor and the and vector, let's write the tensor in the 9 element like this, and we can write the vector b. To get the result in the first row, multiplied by elements in the vector and sum each other. Then second one, same thing, and third one, the same thing. Then we obtain like a matrix. The form has the 3 element in the column form. This is the result. This just the result component L1, L2, L3. Okay, we continue our discussion by next uh, topic. The next one is we call the cross product. The cross product between the two vectors is give the result another vector. In here, let's say you have the vectors A and B. The cross product is a vector give the vector C actually here. In here, the length of this obtained C is equal to this magnitude is equal to this area, this plane between the vectors and AB. This is the physical meaning of the cross product. Let's say you have your C, obtained C, the vector is the perpendicular, that means as the angle is 90 degree to the plane created by the A and B. So cross product between the vector B and A is give the minus C. To use the index notation, we should define the permutation symbol. Let's say we call this the permutation symbol here. The result of permutation symbol is the plus 1 if ijk get these orders 1, 2, 3. We call this right hand rule, like this. And 2, 3, 1 and 3, 1, 2 is give the result just plus 1. It gives the result minus 1 if you obtain the order ijk 1, 3, 2, 3, 2, 1 or 2, 1, 3. And if otherwise, give the result of 0. Let's say the cross product between A, B. We just write the vectors here and we get that one, our result. Actually, let's say I and let's say write L I. Sorry, just remove that one. Okay. Okay. AI and BJ and Li, this is the unit vector, and Lj, this is the unit vector of the vector B, and we obtain from here Bj, Eij, K, Lk. This is the result of that one. Okay. For the cross product between the vector and the tensor, we just do the same things and we obtain that result. Okay. Now became the other rules. Just for example, for the permutation symbol identity is a multiplication for the two permutation symbols get that one that result, and these also can be represented by that one. You should be aware these are all totally different vectors rjk, m and k, but this time we have m and p, r and p. Actually it's just one is same in here, two is same, just one different. So okay, the vector rules, we know the summation of two vectors, three vectors, summation with zero vectors, summation of minus vector and multiplication by the scalars and so on. We know from the linear algebra course. Just want to go next one, next slide. This also summation between the vectors and the tensors. You see distribution and scalar multiplication, so on. Tensor product of the two vectors. Okay, let's say we have two vectors multiply each other a b and that product by other vectors give the result the one. So these are trace of second order tensor, you can find from this formula. And okay, the magnitude of the second order tensor can give the magnitude norm by this formula if they are orthogonal each other. actually also magnitude of the any vector can be written by this, and this is also tensor. If let's say if the two vector, let's say you have two vector like this, then you obtain that one. The inner product is 0 because they have the angle of the 90 degree if they are perpendicular each other. So okay, continue. Another topic is, we call this the calculus of the vectors and the tensors. In here I just want to define another concept. Let's call another concept of the position vector. The position vector can be represented by R is specifying the location of the any point in the space, let's say in the tree space. Let's say just I am in tree space x, y, z. Let's say I have just this point in the tree space. This position vector is just represent the position of this point in the tree space. Let's say then this has the components x, y, z, or x1, x2, and x3. Okay, so the magnitude of R is given by the formula is this x1, x2, and x3. Let's give the magnitude of this position vector. The position vector is basically respect the origin like this, called this position vector. Okay, I just continue. Another concept, we call this the vector differential operator. Also another name is the del operator. For example, for the any specific coordinate, let's say rectangular coordinates, delta can be shown like this, plus L2 x2 plus L3 x3 by this form. By definition, the vector differential operation or the del operator doesn't have any meaning. It should be operated on the either scalar or vector or tensor. Otherwise, it doesn't give any meaning. So this should be used together with any of these three. So we can represent the del operator for different coordinate system. Let's say in this cylindrical coordinate system, we can write this is the R here, actually the R L theta 1 over R theta plus L phi is 1 over R sine theta and so on. This is the representation of the teleporter in the cylindrical coordinate. For the spherical coordinate, sorry, we can write this. Oh, actually, this is belong to spherical coordinates. Let me write now for cylinder. This is uh, spherical coordinate. This is cylindrical coordinate. So on. LR is plus sorry, L theta is 1 over R theta and plus LZ 1 over Z. So these are the open form of the del or differential operator in for different coordinate systems. So in here we continue our discussion actually. Okay, let's say we have a tensor is a respect is the tensor is the dependent on the time, we can represent by this, and this second order tensor for the any vector we just represent by v is the dependent on the t. Then we can write this tensor by this form dA over dt for second order. Then we can write this vector dv over dt is the first order. So then if we put to the open form of this tensor is in this by showing the by indices, we can write like this. For the vector we can write this. For the transform of the as a second order is here transformation and in the first order. So okay, so differentiation of the product, let's say you have d over dt and then you have the a dot product b, then we can write this by this form dA over dt dot product by vector b plus a vector a dot product between db over dt. For the cross product is similar manner, dA over dt cross product by vector b and a cross product by the db over dt, and this is the closed form of that one can present. So as we defined before, the defined teleporter can be defined in here. The I in here is the repeated. For the rectangular coordinate, you can repeat the I and you can write your teleporter. Then the gradient operation, if I operate this del on the any scalar, we can just get that one. The gradient is can be represented by this form, and then the partial derivative of the scalar with respect to any coordinates, you can get that one, that form. For the gradient of the vector, we can represent in here, and we call actually this result give the vector, and this give result as a second order tensor if you see from the 2 units vectors. The divergence, we call this divergence dot product between the del operator and any vectors, they give that result. That result is the result of the scalar. Okay, let's continue the curl operation. Let's say cross product between the del operator and the any vectors gives that result. We call this the curl operation. This is the result of the any vector, and Laplacian is the del operator square, and you get the dot product to that one, that form. Then the Laplacian of any scalar is a scalar. You see, other cases, gradient of the tensor is third order tensor. Divergence of the tensor is to give the first order, and basically this is the vector, and curl of the tensor is give the result, and dot product between any vector and the gradient grad v give that result actually. Okay, we just want to continue another mathematical definition from the BSL, the the book we are gonna use in this course actually. The definition of the partial time derivative we call represent by this. Now what is the definition? Suppose we stand on the bridge and observe the concentration of the fish just below us as a function of time. You are here in this point on the bridge. There is a lake here. Just observe the fish concentration below you. Let's say your eye, and you observe the concentration in this area. Okay, so you can record the time rate change of the fish concentration as the fixed location. If you fix your location like this, let's say you define some control volume, some control surface, then you can see the fish concentration change respect to time for the fixed, for the constant xyz, and this is show your concentration change of the fish respect to time. We call this partial derivative of the c concentration with respect to t at the constant xyz. This first definition. The second one, we call this the total time derivative d over dt. Now suppose you are not anymore on the bridge, you just jump on the motor boat and speed around the river. Now you are in the river. Let's say this is your river. You are in the boat like this. You just go around. You just go around by boat, and sometimes going upstream, sometimes downstream, sometimes across the current. All the time you observe fish concentration at any instant respect to time. At any time inside of your river and inside of the control volume, let's say at time is equal to time t1, you are in here. Let's say time is equal to t2, you are here. Let's say time is equal to time 3, you are here, so on. At any time you can show the concentration change of your fish concentration respect to time is given by this formula. Partial derivative of the concentration respect to t by constant xyz plus dx over dt multiplied by partial derivative of the c respect to x by the fixed constant yzt, and so on. These right sides give the instant time rate change of your observed concentration of your fish inside of your river. Okay, in which in here dx over dt, dy over dt, dz over dt are the components of the velocity of the boat. Actually it's coming from the velocity, because you are not your boat is going by some velocity. In the third one, okay, third definition, we just have here the substantial time derivative, and we just represent by big D over dt. Now in the next case, let's say you climb into the canoe and not feeling energetic, so just float along with the current. Now you are in the, again, still in the river, you are in the boat, but you are not doing anything, you are just going with the flow of the river inside of in the river. In this situation, the velocity of the observer is the same as the velocity of the VF stream. So you have some stream of the water here, your velocity is going to be the same as the stream velocity. We call this the V here. And this is which components, and we use the components is Vx, Vy, and Vz. If any instant time, we can report the time rate of change of the fish concentration by this formula. So dc over dt, this time the substantial time derivative is equal to concentration change partial derivative c respect to t, and this term vx multiplied by concentration change of the c respect to x, that one. We call this here substantial derivative. So we can also, this is the open form, we can write also this closed form. We know this from the open form of this that give the result. We know the del operator and then dot product. Then the spatial operator here, underline d over dt, is called substantial derivative, meaning that the time rate of change is reported as one moves with the substance. It is your substance, just the water. The terms material derivative, hydrodynamic derivative, and derivative following the motion are also used. Okay, just move our final slides here. Okay, here I'm just going to define some very important theorems. We are going to use the derivation of the conservation laws. We are going to use in this course actually the Reynolds transport theorem plus all these theorems and concepts to derive the conservation laws. In here, the first one, let's say you have some body, we call this some control volume, you have some control surface, you have some boundaries. You say this is your surface, you represent by S and control volume V. Then you have some very small differential element inside of your system. You pick here, let's say, and this is we call ds because it is very small differential area and it has differential volume, and this show the vector flux vector inside of your body, and this shows the normal vector. The normal vector always is perpendicular to the surface area, and your flowers per area is given by the vector a, ds differential area and differential volume. Then the theorems give the divergence theorems here, double integral of the dot product between the normal vector and the vector a, then this give is equal to triple product the divergence of the vector a. So in physically meaning, the dot product between the normal vector and a is the equal to flow rate to across to s. You say you have here again your s. This give the total flow rate is across to your surface here ds due to the vector of a. So all the direction of the a is the same direction with the normal vectors. So then we can call the total mass conservation of at a point is the continuum. It can given by this formula again. So continue. In the next slides, okay, we just here have mathematical of the description of the motion without regard to physical cause. We have the just position vector we defined before. It's shown xi and li is shown the any position of the any point in the space in here the tree space. The vector here where this can be shown by the substantial derivative versus that one. We define the difference between that one, the partial derivative, that one and that one before. Now we can move here. Okay, now here actually we define that term is the reference point, as another word is the starting point. Then we can write the x vector as depending on the that one reference coordinate reference point. Let's say you have some vector, but initially this vector is, let's say you started from this point, so that your vector is now depending the time and the coordinate reference vectors. Then we say to give the location of t of the mass that, and this at time is equal to 0, we have the mass location in here. This is the time is equal to 0 by show by this vector the reference time. Then x are the spatial coordinates and are the material coordinate. And we have two definition here. Then if we wanna define the location of the vector and mass, for example, the mass inside your system, flowing mass, this show the spatial coordinates, but that one shows the material coordinate. That means time is equal to 0 is show where is your material, like this. You say time is equal to 0, that one, and then you obtain this x when time is equal to t. So change over time does not change over time because this is the fixed, this starting point. This never change respect to time, but this change respect to time. Okay, now continue our discussion here. We can ask what is specific element of mass at the time t. What is it? If you wanna find your mass, element of your mass inside of your control volume at any time t, you'd answer that question. Or we can ask what element of mass is located at the x at the time t. In other words, what is that one? This inverse relationship exists if the Jacobian exists in here. So, okay, the Jacobian is given by this formula. Also, maybe I should write the properties of the continuum in terms of the either. So let's say for the spatial coordinates, let's say you have some raw density of your system. Your density can be written as the dependent of your x and your t. Also your velocity, also your tensor, anything. For the material coordinates, this time your density is gonna be dependent on your starting point and the time, but spatial coordinates is gonna be like here. For example, for the material coordinates, this one is gonna be fixed. It's gonna not change. Like the example I showed before in the like you are stand on the bridge and you are observing the river for the fixed uh, coordinates, but the time is changed. But for this case, this time for your spatial coordinates, you are just going around by some boats, and we can show here another one. So we defined before this partial derivative for the constant x, this derivative with respect to time while holding x constant, as I observing the fish concentration when it's standing on the bridge, change over time while fixed at a single point in the rectangular coordinates. Define this is the substantial derivative. This time you have partial derivative is with constant fixed starting point reference coordinate derivative with respect to time while holding that constant while moving with the mass. This time you are moving with the like Kona and you don't just move. This time the over dt is the total derivative, is the neither that one or neither hold the constant. Both of them is just moving, like you have the motorboat and just go around the river. At any time you can observe the concentration. So these are the three different definitions again. So useful question is how are these different various derivatives related to each other? Now this next two slides is gonna show the relation between these two. So write this one is like this dependent x and t, and we can write that one is dependent that one. Okay, this is the this is the actual spatial coordinates. This is the material coordinate. In here, that one, the property of interest. Let's say the interest just you have your system. You just interest like a consider again the river example. Concentration of the fish. This is the property of your interest, and these are the functions of that one. See, because your concentration inside of the fish concentration depends on either x or t or that one or t. So we can write that one by this formula, by chain rule. partial derivative of that one respect x dx, partial derivative respect t and dt, or we can write that one in similar manner by this chain rule, by this form, divide by dt at constant t. So if you divide every side by dt at the constant, that one, starting coordinates, so if you continue here, if we divide, take this equation here, let's say dE equals E divide by dt, like by the constant, and the right side xi is divided by dt by constant, plus you can write that one also, dt over x plus dt over dt. So this gives the 1, and here that one is from the previous slide is equal to the xi dt, and we can obtain that one. These also equal to, from the definition of the previous slide, that one also equal to that one. Then I can also, this is the definition of the velocity, and I can write then this term is equal to that term here. I can write these terms by the del operator in this form. So we call this final form is the material derivative. This is very important relationship. We are gonna use this later in the derivation of the conservation equation. Similarly, if I wanna use that one instead of that one, provide this relation here. Show again where this equation come from. If we go previous that one you see here, these are the equal, these are the equal each other. So in here you just use this relation. Okay, now the objective is to obtain the vector tensor equation where the conservation laws and mass generation is equal to 0, energy generation 0, momentum, linear momentum generation 0, angular momentum 0, plus second law of thermodynamics, the generation of the entropy either equal to 0 or greater than 0, it cannot be minus. So on non-conservative accounting relation, so okay, so mechanical energy balance and thermal energy then balance. So after all this concept and the definition, one more thing we need to review the Reynolds transport theorem. After the review the Reynolds transport theorem, the next video we are just gonna jump in the chapter inside of the BSL, and we just start from the momentum and to go to the mass and then the energy, and we're just gonna derive the conservation equations by using all this concept and Reynolds transport theorem. And see you in the next video.